Hello, everybody, and welcome. I'm just waiting. They said there might be a red box. I don't see a red box, but I see a red circle. So I'm going to assume that the circle is the box for the purpose of the live stream. So hello, everybody, and welcome to my talk, Plain Text, at DDD Online, or DDD 2020, or DDD, whatever DDD we're calling this event. And yeah, it's been kind of a weird year. Lots of people have spoken about that. It's nice to be back at DDD, even virtually. Always been a really, really, really fun event. Just a little bit of preamble about the event itself. Code of conduct, for those of you, obviously it's an online event, so people are kind of dropping in and out throughout the day. Be aware of others, be welcoming, be respectful. Remember that you're just typing into a screen, but there's real people on the other end of it, and some of them are having a pretty rough time this year. Be friendly, be patient, be open, be kind. As long as everybody is kind, I think this will all probably be fine. Donate. So the National Museum of Computing this year has been horrible for all kinds of institutions, like museums, art galleries, live music venues, theaters. And one of the institutions that has been affected is the National Museum of Computing, which is at Bletchley Park. It is an amazing place. They have all sorts of one-of-a-kind computers, a prototype of a thing called the Witch, which was a one-of-a-kind analog computer that was built for weather simulation. And they're struggling, so go over here and give them all of your money. Don't buy your family Christmas presents. They will only waste them. Give all your money to the Museum of Computing and tell them DDD sent you. Our sponsors, thank you to all of them for making all of this happen. Black Marble, Microsoft Sage, Grey Matter, NDC London, source very close to my heart. Go out and check them out. We're putting the program together for that at the moment. There's quite a few people here today who are speaking at NDC London, including me. So go and check that out. Landmark IO, University of Hull, thank you all of you for supporting us. This would have been a very easy year for everyone to go, now we're not sponsoring anything. So all the companies who've stuck with us to make things happen, that's amazing. Thank you for doing it. And let's get some noise out there. Tweet it, hashtag DDD2020 at Developer Day. Get some noise out there. Let people know what they're missing out on, because they don't have to miss out on it. They can literally go on the website, click the link, and they can join the sessions this afternoon, and we can get word out, we can get more audience, we can get more people. And on that note, it is time to talk about the fact that I have just started the wrong slideshow. Because I have a slideshow that is mine, and I have a slideshow that is the DDD intro slides that they sent me this morning, and I pasted the one onto the beginning of the other. There we go, that's better. So hello, yes, I am Dylan Beattie. I run a company called Ursatile that I set up in January to do lots of international travel and software and workshops. And I believe the expression is pivoted in response to market conditions. I run online training. I teach people distributed systems, JavaScript, .NET systems architecture. Check that out at ursatile.com. I'm about to stick up a whole load of workshops for next year. All of you out there, you got training budget you need to spend by the end of the day you haven't spent yet? Check back next week. I'll give you something to spend it on. I'm a Microsoft MVP. Thank you very much, Microsoft. That's awesome. And also to all the companies who give MVPs free licenses and free software and things. You're all brilliant. I run a .NET user group in London with Ian and Liam and a bunch of other people who you know. And I also invented a programming language as a joke that became a joke with a formal reference implementation and a project plan. It is a language called Rockstar. It exists so that anybody who wants to can be a Rockstar developer. Go to codewithrockstar.com, type in shout hello world, click rock, and congratulations. You're a Rockstar programmer. And today, I'm going to talk to you about plain text. Really? Yeah, really. Absolutely. Talk about plain text. Now, asking programmers what they think about text is like asking fish what they think about water. They're like, what? No, it's just stuff, isn't it? It's just, we don't need to think about that. But like a lot of technology, to get value out of technology, we need to solve three problems. Somebody has an idea, a thought, a concept, a problem, something that to use technology to solve. So we need a way of getting that idea into the technology. And then the technology needs to do something with it, which we tend to call processing. And then for anything meaningful to happen, we have to get something back out of the technology at the other end so that another human being can go, ah, I see. I get it. And plain text is no different. Now, we're going to start right at the beginning. Humans invented writing about 5,000 years ago, but it was all a lot of tedious nonsense involving quill pens and, hieroglyphics until we had the bright idea, what if we combine the writing with electricity? And that's where we got probably the first electrical communication systems in history. First one that was ever actually used was this thing, the Cook and Wheatstone telegraph system. It was used in England in the 1930s. And there's a couple of really interesting things here that will be familiar to anybody who works in technology. So first of all, Cook and Wheatstone were two people. Cook was a business person. Wheatstone was a scientist. Wheatstone wanted to give everything away for free. Cook said they had to charge lots of money for it. Cook thought that everything needed to be user-friendly. Whetstone said you should have expert trained operators on the system so you didn't need to worry too much about making things user-friendly and accessible. Those conversations are just uncannily familiar, even nearly 200 years later. Open source versus closed source, user experience versus getting people trained up to use the thing properly. But the really interesting thing about the Cook and Whetstone system, it used 5 cables. So they would run a bundle of 5 wires about 20 miles along a railway line, and they'd have one of these devices plugged in at each end of it. And they were adamant, or one of them, Cook, was adamant, that you didn't need trained operators. Anyone should be able to read the telegraph system. So the way you sent a letter is you would wire up one of these letters to the positive terminal of your power supply. You'd connect the other one to the negative. That would create a circuit. So one wire would now be positive, one wire would be negative, which meant 2 of those needles would deflect. And they would point, and where they intersected, you would read that letter off the telegraph system. Only supported 24 letters of the alphabet, but that was enough to revolutionize communication. This was the first successful telegraph system ever invented. It's also the first text encoding system ever invented. And it was a 5-symbol trinary encoding system where each letter of their 24-letter alphabet was assigned a 5-symbol code where symbols could be plus, minus, or 0. So you think ASCII and EBCDIC and Unicode is complicated? 5-symbol trinary encoding system. Let me just switch the Q&A over here because I'm looking at new, not published, which means I only see things until they're approved and then they disappear. Now I can see published, so I'll see stuff after Rick clicks the big put this on the internet button. So now I need to switch my focus back to PowerPoint. This was all a lot easier when we just got to do it in big rooms, you know. Anyway, the encoding system you've probably heard of is this one, Morse code. This was not invented by Samuel Morse. Morse invented an encoding system which looked a little bit like what we know as Morse code, but it had variable length symbols. It was designed to work on a single wire. The biggest problem with Cook and Whetstone is you've got 5 wires. One of them burns out. Now you can't use it anymore. So it failed 5 times as often as a single system. It had, redundancy, but none of it was actually redundant because you needed all 5 wires. It was multiple points of failure. Samuel Morse invented the first single wire telegraph system, but it was a German engineer, a guy called Friedrich Gerke, who standardized Morse code. He took out variable length symbols. He's like dots, dashes, that's it. That's what we're going to use. And in 1865, there was a conference, an international telecommunications conference, like DDD, only very, very kind of old in history. It was in Paris, and they agreed that Morse code was the standard for international telegraphs. And it was a big deal because the telegraph network was just about to take off. Countries were wired together. They were just about to run the first cable across the Atlantic. And if you've ever worked in tech, you know that when nobody is using your stuff, you can do anything you like. No users, hey, change this, change that, remove that button, put this feature over there, change the protocols. It doesn't matter. No one's using it, so no one cares. So there's no backlash. Once people are using your stuff, you can't change anything ever again because you're going to upset the users. So once Morse code had rolled out as the dominant communication standard for the entire global telegraph system, it was almost impossible to change it ever again. Morse code is still used today in the same format that was ratified in 1865. But eventually, something came along that made them go, it might be time to rethink some of these decisions. And that was computers, digital computers. Digital computers didn't work well with Morse code. It wasn't an efficient format for reading, writing, or storing. So a bunch of smart people, they were mostly American men, but they were still pretty smart. They sat down and tried to solve this problem. And they came up with ASCII, the American Standard Code for Information Interchange. Now, the 2 things you've got to realize about ASCII as we start digging into it. 1, ASCII was designed to work on these mechanical teleprinters because, cathode ray tubes and display units were still pretty rare at the time this was ratified. And 2, ASCII was designed to work with these punch cards. Good old-fashioned technology. Now, I'm guessing most of the people on this call have probably never seen a teleprinter or a punch card, but we are still living with the consequences of these design decisions probably every time we open any application on any of our computers. Let's have a little whirlwind tour of the ASCII character set. So the first block, ASCII defined characters from 0 to 127, 7 bits of encoding. And it started off with 0, all the zeros, that's a null character. Anyone who's worked with C will know what that is. Then the basically rest of that block is control codes for controlling teleprinters. And you're thinking, yeah, big deal, nobody uses teleprinters anymore. But there were shortcut keys for entering these characters. If you wanted to send an ASCII 1 start of heading, you pressed Control A. And if you wanted to send a start of text, you pressed Control B. And if you went, oh, no, stop the text, that's a problem, you press Control C, which was the shortcut for ASCII code 3. And that survives today. When you accidentally write an infinite loop in your Advent of Code submission and you have to kill it before it eats all your resources, that's why we press Control C. There's a bunch of others in here that we don't really know very much. Control G, which is the ASCII bell character. That one's kind of fun, because if you open a terminal window on a Windows machine, you type echo space, press Control G, press enter, it will go bing, because that's the same control code that used to be used to ring the bell, the physical bell on a teleprinter system, and it still survives. If you want a console window to make a noise, echo a Control G, echo a bell character. Now, there's a couple in here that a lot of programmers are familiar with, which are the carriage return and the line feed. This is 13 and 10, respectively. Now, the thing about a mechanical teleprinter is it would print a line of text with a little thing called a carriage. And when you got to the end, you needed the carriage to return to the start of the line, and then you wanted to feed the next line up into the printer. And these things were not always used together. If you wanted to do bold text on a mechanical teleprinter, you'd print a line of text, and then you would carriage return it, and then you'd print the same line of text again, and it would overprint it, and you get this kind of pseudo bold effect. So carriage returns were used without line feeds, and sometimes line feeds were used without carriage returns if you wanted to put a row of characters straight down the middle of a sheet of paper and stuff. And so we have all these interesting little quirks of history. Now, if you've ever done work on Mac OS or Unix or Linux systems, you'll know that a carriage or an end of line character in those is a \n. Whereas Windows developers, we say, no, carriage return new line, because you have to send the carriage back to the start of the line, right? Now, the reason for this discrepancy is that the modern Linux and Mac OS evolved from Unix, and Unix evolved from a system called Multics, and Multics was the first operating system in history that supported device drivers. First operating system ever where you could say, look, if the teleprinter wants a carriage return and a new line separately, that's the teleprinter's problem. We'll use a driver to do that, and then our text files can just say new line /n. Windows 10 evolved from Windows 7, which evolved from Windows 8, which evolved from Windows 7, which evolved from XP, which all the way back to Windows 95, which evolved from MS-DOS, which evolved from CP/M, and CP/M was built to run on cheap mini computer hardware that didn't have any device driver capability. So if you wanted the carriage to go back to the start of the next line, you had to send 2 instructions. And so here we are nearly 50 years later, and we still can't agree on how to end a line. Of course, .NET, we solved that by we've got environment.newline, which magically works except in all of the very, very common cases where it doesn't. I've been doing Advent of Code this week, and the text files that they give you were made on a Unix system. So you download a text file from the internet, and then you go split that file on environment.newline, and it goes, no, that file's environment is not my environment. I'm sorry, I cannot help you here. So you have to strip the /r's out and stuff. Look at another chunk of ASCII. So the next block we got space, exclamation mark, quotes, punctuation. Now, there's a lot of punctuation marks that they use in typesetting and book publishing that just kind of fell by the wayside for a couple of decades because ASCII didn't support them. You know how many kinds of dash there are? Because there's a minus sign and there's a hyphen. There's a thing called an N dash. There's a thing called an M dash. And in book publishing, they are all different characters that are used for different things. And with the advent of screen readers and widespread Unicode support, we're starting to see some of these really nice typographic conventions come back into digital software. But ASCII was just like, nah, hyphen. That's all you get. Dash, minus, hyphen, N dash, M dash. A hyphen is good enough for anybody. And so there's a kind of some obscure typographic characters that just everyone forgot about for a while because computers couldn't deal with them. Then there are the numbers, the decimal numbers. Now, the brilliant thing about these in ASCII is if you want to translate from a number to a string or a string back to a number, you just look at the bottom 4 bits because that's the numeric value of that digit. And early computers, even, old 4-bit and 8-bit computers could do this really, really fast. You just ignore the top half. And if you want to turn it back into a string, you put 0011 on the beginning and bang, there's your ASCII character at the other side. Then we get into the alpha block where we've got the letters of the alphabet. You ever wonder why A is 65 and lowercase a is 97? It's because they're 32 characters apart, which means they're separated by 1 bit. So if you want to do a case-insensitive comparison in ASCII, you just ignore the 6th bit, and then the big A's and the little a's are the same, and you can do case-insensitive sorting on your text files. And right at the end of the block, we got a little bit more mopping up some leftover punctuation, and then we have del 127, the ASCII delete character. It's a block of ones. The reason it's a block of ones is because if you want to erase a punched card, the only way to do it is to punch out all the rest of the holes so you can't read what was there before anymore. And that's why ASCII del is a block of 7 ones. It's the thing that would punch out a punch card. If you printed dels onto every row of a punch card, it would fall apart and it wouldn't run through the gears anymore. So you could actually DOS a mainframe system, denial of service a mainframe system, by deleting an entire punch card and then running it through again. So if you ever get sent back in time and you need to take down ARPANET, there you go. You learned that today. So the Americans congratulate themselves on their victory and they roll it out. Hey, 127 characters is all you'll ever need. And the rest of the world goes, what? We can't work with this. What? Now, people adapted in different ways. I grew up in Zimbabwe, so my childhood spoke English, dollars, cents. It was culturally quite similar to America, even though Zimbabwe used to be a sort of British colony and things. So my first experience of character encoding was when I moved to the UK when I was 10 years old, and I was using WordPerfect for DOS, and I wanted to print this in my homework. And I couldn't because it wasn't there, because this is not one of the characters that the Americans cared about in 1965 when they ratified ASCII. And a lot of people were having similar headaches. Some countries were like, well, we can almost do it. There's just these 2 or 3 letters in our alphabet that aren't there. Some cultures, Korean, Arabic, Hebrew, were just going, we can't even, where do we even begin? Japanese came up with a thing called Romanji, which is a way of writing Japanese using American ASCII, which is really, really quite interesting. But what a lot of people did is they went, hang on, we got 8 bits in a byte, and ASCII's only using 7 of them. Hello? Is anybody using this bit here? And of course, nobody said, yes, we're using it. And so everyone went, all right, we'll have that bit. And about a couple of 100 different ideas all over the world all sprang up going, we've got a good idea for how to use the second half of ASCII. And different countries, different companies, different alphabets, they all came up with their own incompatible ideas about what the second half of ASCII should be used for. One of the most famous ones ever was the one that shipped with the IBM PC. These things are called code pages. A code page, you ever come across that? A code page is a set of rules for saying, this is what the top half of ASCII means right here, right now in this document on this system. And IBM PC shipped with code page 437, which included all of these accent characters. Now, the interesting thing about 437, it includes most Western European accents, and it includes the half of the Greek alphabet that is used in physics. So you can't use 437 to write Greek, but you can use it to write physics equations, which I thought was a slightly weird compromise. And it has, block and line and box drawing characters, which if you ever played any text mode games on a PC, you'll remember these. They also took the bold step of trying to redefine that bottom block of control codes, because they're like, we don't have teleprinters anymore. These things don't matter. Now, if you've ever seen an IBM PC crash really, really hard, it would do it with a kind of multicolored chaos of smiley faces and playing cards. It's because the operating system is throwing out control code characters and the display is going, oh, you must want to draw smiley faces and playing cards. So that's how that works. Code pages were a bit of a mess. If you go on Wikipedia today and you look at the list of code pages, there's about 100 of them maintained by Apple. There's several hundred maintained by IBM. Microsoft has some. Microsoft has some for DOS and some for Windows, and they are not always the same. Different countries and cultures have different code pages. Now, this kind of wasn't a big deal when it was just you doing your job on your computer and then printing it on your printer and handing in the report. But once we started connecting the computers and the people together, we needed a better system. We needed a unified encoding system. And so the bright sparks at the Unicode Consortium said, I have an idea. I think we can fix this. The Unicode Consortium's mission statement is fantastic. It just says this: to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Deconstruct that a little bit, a single consistent way. Any character, we should be able to look at any shape of any letter in any word in any alphabet, and Unicode says, yes, it's that one. That's the one that is. All human languages, not just the ones that we speak today, but ancient languages as well. Archaeologists use Unicode to document their research. Egyptian hieroglyphics, ancient Sumerian, all these kinds of languages have to be included so that archaeology and historical research don't get left out. And across all computers and devices, well, how do you do that? Well, the only way to even attempt to do that is you've got to come up with something that's brilliant. You've got to come up with something that is literally the best possible solution to that problem. And you've got to make it free and implemented everywhere so that when people are building computers, printers, mobile phones, tablets, they're like, yeah, of course we'll support Unicode. It's free and it's good. It solves our problem. And it means we can play nicely with the rest of the planet. Here are two strings. Do you think these strings are equal? Because they look the same, and you're sort of looking and you're not quite sure what that is. Let me show you the rest of these. Are substrings. These aren't actually strings. If I show you the substrings here, that's what we're dealing with. Now, the top one there, this word, if anyone reads Russian, this is хорошо. This means good. Yeah. The bottom one, exoplanet. That's an English word. So these are the same shapes. But in Russian, that's XOR. In English, it's XOP. Are they the same letters? Well, obviously not the same letters, the same shape, but they make a different noise. What about me? So the top one here, the me is actually Menya Zavut Dylan, which is Russian, means my name is Dylan. The bottom one is English, meetings are cool. But it's e in both cases. It's the same me kind of sound. Are those the same letters? They're the same shapes that represent the same noise, the same phoneme, but in a different alphabet. Should they be the same letter? These are the kind of questions that Unicode had to try and solve. Now, the decision they made is they are going to respect the integrity of alphabets. So the me there and the me there, those are different letters that come from different alphabets, which are different sections of the Unicode code point system. Because even though about 15 of the letters in Russian are the same as the same shape in English, they're separate. One is the Russian alphabet, one's the English alphabet. Same thing with the Greek alphabet. Same thing with all the various different alphabets and encoding systems and stuff. Now, let's have a look at this word here. Now, I am English, I'm British. I see a word like this when I'm traveling. And what my brain does is it goes, hey, I can read that. I don't know what those things mean, so I'm just going to ignore them. And I'll go to the front desk of the hotel in Norway and I will ask them for a harphoner. And they will roll around laughing because that is not an A and an O. That is a hårfjerner, I believe is the pronunciation. It's a Norwegian word for a hairdryer. But these are different letters of the alphabet. In English, we just think it's an A with a circle on the top that's kind of optional. In Norwegian, it is the letter O. And this letter occurs in Danish and Swedish and various other languages. So we have these different ideas. Does the circle on the top, does that make it a different letter or not? Well, it kind of depends who you are, where you are, and what it is that you're reading. So I travel, I read things in British, everyone laughs, I get the beers in, which in Norway is a significant investment, and everyone gets along famously. But it is not always quite that simple. Let me introduce you to some friends of mine. This is Francois Bordet, who's an archaeologist from France, and this is the rock band Motley Crue. And if you were to document a particularly interesting rock and metal music festival, you might write the sentence, Francois the archaeologist went to the Motley Crue concert. Now, this is an English sentence. This is definitely written in English, but look at these characters here. We've got the S with a little tail, a little hook underneath, a sedia. We've got an A and an E that have been run together into this ligature shape. We've got an O with an umlaut. We've got a U with an umlaut. Now, the sedia there, that is a loan letter from French that we've pulled across into English because when Francois says, I'm Francois, we respect that. The A and the E, that's an old-fashioned typographic convention. And the umlaut there, that is called the heavy metal umlaut, and it is stupid. And it is pointless. And the first time Motley Crue went on tour in Germany, where the umlaut is actually a thing, they didn't know why the audience were going Mötley Crüe, until someone explained that that's what Mötley Crüe actually says when you write it like that. Now, making Motley Crue look stupid is not a big deal. They look stupid anyway, but sometimes these accents can actually cause real problems. introduce you to another friend of mine, Magnus. Magnus Martinsson. But this is not Magnus Martinsson. This is Magnus Mortensson. There's that little A character again. And Magnus is Swedish. And a couple of years ago, Magnus was traveling to a conference in the United States on a Swedish passport. And the rules of Swedish orthography, the rules that are followed by the Swedish passport company, say if you need that R sound to be rendered into plain 7-bit ASCII, it comes out as A, two A's next to each other. Whereas the people who had printed Magnus' airline ticket, they don't care about the rules of Swedish orthography. They just take the little circle off. And so Magnus ends up trying to get into the US with a passport that says MAA and a airline ticket that just says A. And of course, the US Border Control are very cosmopolitan and understanding people. He had to answer some fairly difficult questions in a little room for a while. Now, he was okay, he got in. But, Magnus is a kind of charming, affluent white guy on his way to a software conference. Imagine how many people that would have played out really badly just because we can't agree on how to turn somebody's name into ASCII and put it on an airline ticket. Do you still think there's such a thing as plain text? Let's keep going a little further. Here is a list of places, a list of cities in Europe that we have been asked to put into our database. And so we are going to declare a cities table, and we are going to insert into cities Berlin, Aachen, Zurich, Aarhus, and Örebro. And then we are going to select star from cities, and there it is. It's come back out in the order that we put it in, all nice and easy. Let's check, select star from cities where name equals Örebro. What? It's not there. But we just put it there. You saw it, right? The reason is this database currently does not think that Örebro and Örebro are the same place because we have told it that the umlaut is important. So what if Örebro is Örebro? Yes, no. Oh, of course, the umlaut. What we need to do is specify a collation, a set of rules for deciding which strings are greater than, less than, or equal to other strings. This collation is Latin, general, case insensitive, accent insensitive. If Örebro equals Örebro according to that set of rules, print yes, brilliant, there it is. Let's go back to our list of countries. Select star from cities, order by name. Cool, all right, Berlin, Aachen, Aarhus, Berlin, Örebro, Zurich. Cool, right. Now, what if we say do that according to the rules of Finnish and Swedish orthography, the Finnish-Swedish collation system? Örebro is now at the end, because in Finland and Sweden, an with an O with an umlaut, which is I'm mangling the pronunciation here. That's the last letter of the alphabet. It goes after Z. Now, the Danish and Norwegian collation system, it gets even weirder. If we select from cities ordered by name collated using Danish and Norwegian, Berlin, Zurich, Örebro, Aachen, Aarhus. Aachen and Aarhus are now at the end. AA is after ZU in that alphabet. Does anyone have any idea why this might be the case? Now, people often say, oh, I don't think we should bring politics into technology. I think we could be neutral. Well, the bad news is that politics brought itself to technology a long time before any of us got here. This is Aarhus. Aarhus is the second largest city in Denmark after Copenhagen. And from 1948 until 2011, Aarhus was officially spelled Aarhus, but with an A with a little circle on the top. In 1948, in the aftermath of World War II, Denmark decided that it wanted its spelling to be less German and more Swedish. So they added 3 letters to the Danish alphabet. They added these 3 letters to the end, and they made a rule that said any place names, people's names, anything that used to be spelt starting with AA is now going to be spelt with this new letter that we've added to the alphabet. And that goes at the end of the alphabet, and so this was then in alphabetical order. Then in 2011, the people of Aarhus decided that the A with a circle on the top was interfering with their Google foo, and they were going to change it back to Aarhus AA. So we now have a rule where in Denmark and Norway, anything that starts AA that's a place in Scandinavia goes at the end of the alphabet, because obviously that would have been or once upon a time. But anything with an AA that's not in Scandinavia goes at the beginning. So Aachen is in Germany, so that stays at the top. But Aarhus is in Denmark, and that goes to the end. And you're looking at this as a developer, and you're going, those are literally the same characters. Like, how on earth do you expect me to get this stuff right? Well, if you ever find yourself having to do this, you've just got to override it. You've got to include another column in your database that's like, this is what we show the humans, And this is what the humans think they're looking at. So this is what we're going to use to sort these things and make sure that they're in the correct variation of alphabetical order we've got here. And if you add a sort name column and you run it based on that one, you will get the correct thing coming out of it. So what this just kind of goes to show, if you try and find the technology which is genuinely independent of politics, there is none. All of the stuff we do every day, we're working on systems that were built by people, and Unicode is just another example of this. Very, very successful technology embraces the things people are already doing. It does not encourage them to do something different. It doesn't force them to do something different. You know, dictionaries' jobs are not to tell you how to speak English. They are to tell you, well, this is how people are speaking English. These are the words that are happening, and this is the context they're being used in. You know, literally now means the opposite of literally, because people are like, it literally exploded. And it's like, no, it didn't. But now we use that as a thing, you know. And Unicode is the same. They didn't set out to regularize spelling. They just set out to go, look, this is how humans behave. Let's see if we can give machines a way of working with this more effectively. Well, let's go back to Francois, the French archaeologist, and this little "s" in the middle of his name. Now, this has a code point in Unicode. Unicode says that this character here, if you're speaking French, is 00C7 is the code point for this. It's a hexadecimal identifier. But Unicode also says if we're typing in English and we want to talk about Francois, we're going to use a regular English letter C, and we're going to stick a little cedilla underneath it. And the cedilla here, this is Unicode 0327. This is a combining accent, a combining cedilla, which is a Unicode thing that says whatever character you just drew, stick one of these on it. Now, you can add one of these. You can add two of these. If you really, really want to, you can add lots and lots and lots of these to a single character, and most browsers and handsets will have a really valiant stab at rendering them, and you end up with Zalgo. He comes, and Tony the Pony gets very, very afraid at this point. This is how Zalgo text works. It's regular ASCII with a whole bunch of Unicode combining characters stuck all over it. But, you know, the logical outcome of this, there's two different ways of saying Francois in Unicode. There's the top one and there's the bottom one. And the top one, the C is a single character, and the bottom one, it's an English C with a cedilla underneath it. How do we know if they're the same? Because a lot of the stuff we do with computers is about, hey, is this text in that document? Is this word in that dictionary? Is this text string on that internet over there? And if we can't even decide if two strings are the same, we can't do searching, we can't do sorting, we can't do filtering, we can't do all kinds of things. Now, again, what Unicode tried to do is they said, well, look, what are the humans doing? Can we just kind of look and come up with some taxonomy around that? And they come up with a system called Unicode normalization. And there are 4 different forms. Unicode says that there are 4 different ways of looking at two strings and deciding if they're the same. Actually, what there are 4 different ways of taking a string and turning it into something that can be compared. And these are normalization form C and form D. C stands for composed, D stands for decomposed. Composed means squash it all together into the smallest number of code points you can. Decomposed means stretch it all out into the biggest number of code points that you can. And then KC and KD. K here stands for canonical. It's like, never mind the shapes, what is the meaning of the letters here? Let me show you a couple of examples. So there's a little snippet of code here that I'll share afterwards. This is some .NET Core, or just .NET 5 Framework 5 Core, whatever we're calling it now. This is some .NET code in C# for comparing strings. And what I'm going to do is I'm going to build 2 strings by sticking together some character arrays. And I got my friend's Motley Crew in here. Now, the top one, I've got the M, and then I've got the with the umlaut, and then I've got TLEYCR, and then the bottom I have M, O, and then Unicode 0308, which is a combining diaresis. Put an umlaut on whatever you got. It's basically like a heavy metal power-up for English text. So when I run these 2 string sequences through my comparison function, what I get at the other side is I get 2 strings. They're the same length. They are not equal. If I do S1 equals S2, but under all 4 different kinds of Unicode normalization, they are the same. If I compose them, I end up with the same thing. If I decompose them, I end up with the same thing. Now let's have a look at a different example to show you the difference between these. Take these 2 strings here. So Unicode includes a set of letters in circles as a separate chunk of the code point map that they've got there. So I can write plain text as ASCII, or I can write plain text by using these little letters inside circles. And this is how people get those weird nicknames you see them using on Twitter and stuff in places where you're like, but you can't put fonts there. How did they do that? Now, if I compare these ones using my comparison function, First of all, you'll notice that the capital P and the capital T in the first bit, they got mangled because those glyphs didn't survive the round trip from the code to the .NET console and back into PowerPoint. But you'll see that S1, S2, same length, they are not equal. Under C and D, composition and decomposition, they are not equal. But if we say, please interpret them canonically, it says, well, yeah, obviously that's a P and that's a P, and they're both English letters. So this is the same word written differently. So this canonical string comparison is what you need to use if you're looking for someone on Twitter and they've spelt their username with these funny little letters in it. Now, a couple of years ago, I was at work one morning and one of my team came over to me and said, dude, I think we've been hacked. Now, if you work in IT, people get hacked all the time. They're like, I've been hacked. No, you haven't. You've just, that's an attachment to the email. Go back, click that thing. I've been hacked. No, you haven't. This is Microsoft Teams. I've been hacked. No, you've just accidentally opened the inspector in Google Chrome, you know. But this person was a very, very capable security engineer. I was like, all right, why do you think we've been hacked? There's Chinese in the event logs. And I have a look at it, and he's right. There is Chinese in the event logs. Now, we do not do business with China. The office was near Chinatown, but that's it. No Chinese customers, no Chinese content, no Chinese trade deals, none of this kind of stuff. So I'm like, how did we get Chinese in the Windows event log? So I said to one of the team, look, go through the whole database, look for any of these characters, see if there's any of this in any of these records. Somebody else, can you check the firewall logs? You look at this. And you know, me being in charge of the team was like, right, all the important work has now been delegated to somebody who's unlikely to be interrupted. Now I can go and I can complain on Twitter about the kind of day that I'm having. And the nice thing about having lots of people follow you on Twitter is when you do this, the internet solves your problems for you. And I get these comments pop up. And David McBride says, oh, that looks like a Unicode mapping error. And then the fake Unicode Twitter account says the low bits are null. So this is probably UTF-16LE been mistaken for UTF-16 Biggie, UTF-16 Biggie, BE. At which point I go, yeah, and I nod like I have any idea what 16LE and 16BE mean. And then I do probably the most intensive crash course in Unicode character encoding in the history of human beings. And what I learn in the next sort of 20 minutes or so, Microsoft Windows and Java and JavaScript, internally, all characters are stored as 2 bytes. They are stored as 16 bits, UTF-16. Now, the problem when you have 2 bytes is you need to decide which one comes first, the bigger one or the smaller one, big endian or little endian. If you take the string delete and you type that into a Windows computer, what Windows puts in memory is this string of bytes. We got a 0 and then a 44, then a 0, then a 65, then a 0, then a 6C, then a 0, then a 65. But if you flip those round backwards, and you render them back out, you get this. You get Chinese. You get the first character there is a Chinese character meaning to put a pearl in the mouth of a deceased relative. So that didn't get us very far in trying to work out if this was maybe a ransom note from some hackers or something. So, okay, we knew where the text was coming from. Question is, how did it get there? Why did it get there? Well, it wasn't that something had flipped the polarity of our dynamic CRM database system. The problem was a faulty network switch, which was dropping 1 byte from that byte stream about every 10 minutes. And when it dropped a byte, everything would suddenly shift over to make up for the missing byte. And so all these characters would get an off by 1 error in the encoding stream, and they would come out as Chinese. So that was the day I discovered UTF-16. And then I started digging. I was like, well, we've got 16BE, 16LE. What else is there? Is this really the best we can come up with? Now, the system that dominates the World Wide Web is a thing called UTF-8. And UTF-8 is brilliant. First thing UTF-8 said is if it's a byte that starts with a 0, it's 7-bit ASCII, the same as it was in 1965. We are not going to try and reinvent that. We're probably stuck with that for the future of humanity as a species. But if it's a byte that starts with a 1, it is part of a multiple byte encoding sequence. Now, multi-byte encoding sequences, they always start with a 1-1, and then all the continuations are 1-0, 1-0, 1-0 until you get to the end of the string or the end of the character. So we look at this example here. 1-1-0 means this is the start of a 2-byte sequence, and then 1-0 means this is the rest of it, and then the red X is here. That's where you put your number. That's where you put your code point. If you need a 3-byte sequence, 1110, 1010, absolutely fine. You need a 4-byte sequence. Now, UTF-8 kind of stopped there because they needed to round trip with a thing called UTF-32, which you can probably work out is like UTF-16, but it's 32 bits instead of 16. It's a 4-byte encoding system, which Windows and Java will also support natively. If you get up to the point where you can't fit stuff in 16 bits anymore, You need to use UTF-8 or you need to use UTF-32. There is actually a UTF-7 as well, which will put Unicode into 7-bit email headers. It is the most horrible encoding I've ever seen, and I am not going to tell you about it. But if you're relaxed and happy and wanted to stress yourself out a little bit, go and read about UTF-7. Now, I mentioned at the beginning, Unicode wanted to document all the human, or to encode all the human languages that had ever been used, including historical ones. But it actually turns out it's not just history that's a problem here, it's the future as well. Because humans invent new languages. We invented one not long ago, within the last few decades, that all of you have learned to read and write without realizing that you are doing it. It's a language that was invented in Japan in the late 1990s by an artist called Shigetaka Kurita. And it is emoji. Emoji was a set of symbols that was rolled out on a thing called iMode. It was a Japanese smartphone platform that was a kind of precursor to the mobile web we have today. It was a massive hit in Japan, and within a couple of years, every phone handset in Japan could render this set of emoji characters. This set, by the way, is now in the Museum of Modern Art in New York. And then what happened, what really blew this thing wide open is in 2008, Apple launched the iPhone in Japan. Now, you couldn't launch iPhone in Japan. You couldn't launch any phone in Japan that didn't support emoji because no one would buy it. So Apple had to add emoji to iOS, which meant everyone else in the world suddenly realized that if they change their region to Japanese, they can send emoji. They can unlock these extra keyboards. At which point the rest of the world goes, we want emoji too. Oi, Android, get with the program. And suddenly, emoji is massively popular. Now, Apple and Android don't collaborate very often. They only do this when it's a really big deal. The two examples I could found, one was the track and trace protocol for the coronavirus pandemic earlier this year. The last time I can think of that Apple and Android formed a collaborative working group was to get emoji into the Unicode standard, which they did, became part of the standard in 2010. It went worldwide, and people started asking questions. Why are all the doctors men? Why are all the people, the kind of Simpsons-y yellow? Why are all the people Caucasian? Why are all the couples and families heterosexual? And, there was, and also questions like, why is there sushi but no tacos? And these kinds of things, because there was a lot of kind of cultural bias baked into the early version of Unicode. In 2015, Unicode took a massive step towards embracing diversity because they came up with a way of changing the skin tone on all of the people emoji. And the way they did it is actually really clever. This is a thumbs up emoji that's been there since the late 1990s. And what they did is they added a set of modifiers for skin tones that say, all right, well, one of these plus one of these it'll render as this on a handset or a device that supports it. And if it doesn't support this combined rendering, you'll just get the two of them one next to each other so that the meaning is still apparent. And this has led to all sorts of really cool, interesting stuff in the emoji character set. Here is the set of emoji that were added to the standard last year. We've got, the chef's kiss in 5 different skin tones. We've got ninjas in a choice of genders and ethnicities. We've got all these different family configurations and different variations on Santa Claus and all these kinds of things. And the way that they have accomplished all of this, they haven't made code points for all these combinations. They've given people building blocks. If you want an emoji of a female astronaut, you take the woman character, then you add in this. This is a zwidge. It's called a zero width joiner. It says add this thing to this thing with no space in between them, and you add a rocket, and you get female astronaut. And if your device doesn't know about female astronaut, you get woman rocket right next to each other. If you want, so this is right here. It's one of my little desk mascots that I got here. This is Mae Jemison, who was the first African-American woman to fly the space shuttle, who the camera is refusing to focus on for various reasons. But she's there. She sits on my desk and kind of laughs at me when I do dumb stuff. And I'm not going to go out and tell her that she can't have her own emoji. And neither was the Unicode consortium. They're like, well, woman plus dark skin tone plus zwidge plus rocket. All right, bang, done it. That works. Now, there's an interesting quirk of all this, which is how they encode flags in emoji. Most of them take, for example, the flag of Belarus. The country code for Belarus is BY. Now, there's a bunch of, there were the letters and then there were the letters in circles. There's also a bunch of letters in something called the tag set in emoji. And the flag of Belarus is the Unicode tag symbol B and the Unicode regional indicator tag letter Y. And that gives you that glyph on systems that support it. England is not a country according to the ISO. England is part of the United Kingdom of Great Britain and Northern Ireland, and the United Kingdom has a proper flag emoji. England has a flag, but it's not part of the emoji flag set. The way you do the England flag is you start with the black flag, and then you add the tag characters for G, B, E, N, G. That's how they do the flag of England, flag of Scotland, flag of Wales, and the flag of Texas, which is the only other non-country regional flag that is part of the Unicode character set. And there is a third kind of flag. The pride flag is a white flag with a zero-width joiner and a rainbow. Now, have a look at this flag here. This is the flag of the Republic of China. Not the People's Republic of China, the Republic of China, which is a country that most of us know as Taiwan. And diplomatic and political relations between Big China and Taiwan, the Republic of China, are strained. There are parts of China where flying this flag will get you locked up as a dissident. Now, if you go onto an iPhone, and you type Taiwan, it'll pop up and you can add the flag of Taiwan in there. Then go into your regional settings and change your location to China mainland. Go back into the text message you were writing. The flag has disappeared and the Taiwanese flag no longer appears on the keyboard. Apple are not going to go to war with China over whether Taiwan gets its own flag or not, because it has so much, there is so much money in China to be spent on handsets that they're not even going there. China doesn't want the flag of Taiwan. All right, Apple are going to take that thing out. Now, if you go on Microsoft Windows, Microsoft has taken an even more sweeping approach to this. Go and look at my profile on Twitter, and I got a little EU flag next to it. Now that flag there, that's being drawn as a PNG by Twitter's web platform. If you go in and edit that as a piece of text, you get this. Letter E, letter U, and Microsoft Windows ignores the fact that that is supposed to be a flag because they're not going within 100 miles of the China-Taiwan thing. They're just like, we're not going to put country flags. We are not getting drawn into whether Kosovo gets its own flag in the Unicode character set. We don't want to get into arguments with someone going, well, they've got a flag and we should have a flag as well, you know. So Windows just sidesteps the whole thing. There are no geographic flags in the Windows Unicode character set support. There are only two flags in Windows. One is the pirate skull and crossbones, and the other one is the gay pride flag. So Windows says no flags allowed, but gay pirates, that's okay. Now, I kind of like Windows, and that's an ethos I can support. Now, one last little detail I want to share with you as we come onto the home stretch is something cool you can do with text that isn't actually anything to do with text. If you have a look at the logo for my company, and you look very closely, you'll see that the T and the I here, they're kind of glued together, like they're not separate letters. Now, that's just ASCII. It's ASCII in a font. The typeface that I use for that logo is called Lato, and it's an open font. I think it's rather lovely. And Lato includes support for something called a ligature. And a ligature was an old-fashioned, in the days of mechanical typesetting, when your printer, when printers were people, your printer sat there at their linotype machine, and they see a T and an I, and they go into a special box, and they get a little metal print head, which was a T and an I kind of run together nicely because it looked good. And this idea of ligatures became part of the TrueType and the OpenType font systems. So when you render the word versatile in the Lato font, the T and the I get run together. Now, here is some source code. Take a little look at this, have a think, tell me what language you think this is written in, stick a comment in the chat to get you warmed up for asking some questions, because we will have a few minutes for that at the end. This is F#. This is completely ordinary F#, but it is F#. Here's the actual code. And if I flip backwards and forwards between those, look closely at the arrows and the pipe arrow indicators there. This is F# in a font called Code. Code is a programmer's typeface that supports ligatures. And all of the common, like the triple equals in JavaScript, it'll turn that into an equal sign with 3 bars. It's brilliant. I love it. And it's available on almost every platform. So if you want to make your programs look really, really cool and make it easier to see if you've double equals where you should have triple equals, go and grab a copy of Code and install that. It's on GitHub. It's open source, created by a guy called Nicky Tonsky. So yeah, go and check that out. Code, ligatures, turn your plain text into beautiful works of art. And I'm going to leave you now with a little traveling story from the days when we could gallivant around the world. A couple of years ago, I was in Belarus, which is a country I love visiting a lot. And the first time I went to Belarus, I was looking around the street and I thought, this is weird. I couldn't read the Cyrillic alphabet at the time. I hadn't really started learning yet. And I was like, I can't read the road signs, and I can't read the menus, and I can't read any of the shops or anything, but I can read all the license plates on the cars. And I did a bit of digging, and I discovered there's a thing called the Vienna Traffic Accord from 1968, the same year as ASCII, where all these countries, including what was then the Soviet Union, they signed a piece of paper saying, yes, if we're going to drive across the border, then we will only use the Latin alphabet on our license plates. We won't use, Hebrew, Arabic, Russian, Korean, any of these alphabets. If you want to sign up to the Vienna Treaty, you're going to use the Latin alphabet on your license plates. And the Soviet Union went, yeah, well, I'll sign that, no problem. Now, Soviet license plates in 1968 looked like this. And people went, but you signed the traffic accord. And they went, yeah. You cannot take a car out of Soviet Union. And I'm like, well, what if we need to? And they're like, they come up with a system. If you could get the travel permits and the papers and everything and a vehicle that would survive the journey, they would give you temporary plates at the border that would be logged in a big book, and you had to bring the vehicle back through the same checkpoint. And if you went back in time, they would pursue you as a dissident who had illegally fled the Soviet Union and stuff. Now, when the Soviet Union kind of, collapsed, ended in the 1990s, most of the former member states of it overhauled their vehicle licensing system, and they came up with license plates that look like this. And we can read these. The top one there, BKAA, so that's a Ukrainian, that's a Belarus. The two bottom ones there are Russian. Now, I'm thinking, but they don't use the Latin alphabet. And then I discovered what they'd done. This is a truly beautiful hack, is they took the Russian alphabet and the English alphabet, and they identified the intersecting set of characters that are the same shape. Not the same letter, they're the same shape. And all license plates in the former Soviet Union states are drawn from that set of letters. It's the set of letters you can type on a Russian keyboard that are also letters in the Latin alphabet. And it so happens that if you take that set of letters and you shuffle them around a little bit, you get the words Pike Matchbox. So next time somebody says to you, I'll send you this file as plain text, you just look them in the eye and say, do you know Pike Matchbox? And if they say, yeah, then you know they've seen this talk. And they know about big endian and little endian and line endings and teleprinters and ligatures and all this kind of stuff. And you're going to be able to have a meaningful conversation about plain text. And if they say, what's Pike Matchbox? Then you have no idea what they are going to send you when they send you plain text. Thank you very much, DDD. That was a lot of fun. We got to close the call in 8 minutes. So we have 8 minutes for questions, comments, interesting commentary, heckling, all the fun we normally have if we were doing this together in person. Now, I tend to assume if there are no questions that I'm just, we've achieved complete enlightenment and total understanding, and everyone now understands everything that there is to understand. But if we got 8 minutes, I can talk about it. I saw someone put in the comments, glad I'm not the only one having that problem with Advent of Code. Advent of Code is brilliant. I'm doing that live on Twitch every day at 4 o'clock every day UK time. I'm trying to do Advent of Code and solve it live on the stream. And it's had some really gnarly little exercises that they've dropped in there this year. Some of them have been fun. Some of them have just been, bang your head against the wall. And it's doing it on a live stream. It's something I always thought I should get better at. Thanks, Edward. Amazing talk, really enjoyable. Yeah, as you can probably tell, it's a lot of fun scratching away at the layers of abstraction and trying to work out why technology behaves the way it does and what are the things that it throws at us and expects us to deal with. But yeah, no, Advent of Code and live streaming, and there's a couple of the examples this year have used recursion, or they've lent themselves to a recursive solution. And I don't know if any of you ever heard of a thing called Feynman's algorithm. Richard Feynman was the physicist who Feynman diagrams and the Space Shuttle Challenger investigation. He published a thing once. He said, well, the way you solve problems is step 1 is you write down the problem, and step 2 is you stare at it and think really hard, and then step 3 is you write down the solution. And that's known as Feynman's algorithm. And some of the, recursion is one of those things that I've never been able to break a recursive solution down into a series of deployable steps. Because it's like, well, it's like kind of putting up an arch, It's like once all the pieces are in place, it'll work. But at any point up to that, the thing is unstable and it will not run. And so trying to do recursion for Advent of Code live on a stream is like, oh, okay, well, I'm just going to stare at this code really hard for about 2 minutes. And then I'm going to write something, and then I'm going to try and explain to you how I got to it, which is interesting. I don't know if any of you caught Dylan Hayes' talk before this one, where he's talking about live streaming and OBS and all these kinds of details. But yeah, there's some fantastically interesting technology out there to play around with and get the hang, and then try and once you've sort of you're fluent in using it, then you can start trying to personalize what you do and bring your own spin into it. So. But anyway, I see no questions, so I'm going to assume a state of total enlightenment has been achieved. What happens now, Rick? So Rick,
I guess since you asked, what happens is I come off mute. You thank everybody for a session well done. We thank you for a very entertaining session that engaged me so much I wasn't paying any attention to anything else. So thank you for that. And when you're ready, we'll end the stream, Dylan.
Yeah, I'm good. So thank you everyone for coming. Don't forget to go and give the National Museum of Computing all of your money. because they need it a lot more than your uncle needs socks. So go and do that, and then send all your family a little note saying, "Hey, I gave all the money to support the preservation of ancient computers because ancient computers are cool." Thank you everyone for tuning in. That was a lot of fun. I hope to see you all online or at something in reality in the not too distant future. Thanks, Rick. Thanks all the DDD team for putting this together. I'm out of here. See you later.